welcome back to our session. We're still investigating terminal potential difference. Right, let's look at the Ohm's law in terms of how it fits into the context of circuit in as far as, terminal potential difference is concerned. Right, so we want to look at the Ohm's law, okay, because we are dealing with circuits that talks about the relationship that exists between potential difference and current. But before we do that, let's remind ourselves of what the Ohm's law says. Right, at this point in time, I also want to emphasize the fact that this is a common question that is asked in terms of remembering skills. The question may come and say, state Ohm's law in words. So you must be able to state the Ohm's law. Very, very important are the key terms that you must include in the definition, as well as you must also use those keywords in the correct context. So this has a lot to do with remembering, which is all or nothing. Right, so what does the Ohm's law say? It states that the current passing through, a conductor is directly proportional to the potential difference or the voltage across the ends of the conductor if temperature remains constant. So what we have underlined is what is very important, or what would refer to as the key terms in as far as the Ohm's law. Right, so the Ohm's law equation says R is equals to V over I. So sometimes we may represent it in this way. So the formula sheet actually provides us with the Ohm's law. Right, so we must be able to copy it correctly and use it where appropriate. So, or we can talk of in terms of the potential difference and say V is equals to the product of current and resistance. So it's still the same equation, but expressed, in a different form. Right. Okay. So terminal is, in as far as terminal potential, terminal voltage and resistance are concerned, we know that the battery has an EMF of E connected to the external circuit, which has some resistance. So this resistance is for the external circuit. But do not forget, the battery in itself has got its own internal resistance, right, which is R. So the external resistance of the circuit in the case of the simulation was the light bulb, would represent that external resistance with capital letter R. So in terms of notation, the capital letter or uppercase R represents the external resistance. It could be a bulb, it could be anything, right? And then with the battery, the internal resistance is denoted by a small letter R, right? Okay. And then what else did we manage to realize? This the difference in terms of the measurements. We knew that when we connected the voltmeter across the battery, when the switch was open, we got a voltage of 12 volts, right? And a current of 0 amperes. That was for the open switch. But for the closed circuit or closed switch, we got a voltage across the battery, right? And we must emphasize on that, of 9 volts. And the current was now 1.5 amperes. So there's no current in the open circuit, while there's 1.5 amperes of current in the closed circuit. But the difference is that also the light bulb is glowing in a closed circuit, while it is not in the open circuit, right? Okay, so we are happy with those reading. So we are saying the battery is not doing work, any work in moving charges in the external circuit or in the internal circuit. So there is 0 current. This statement suggests that current in an open circuit is equals to 0 amperes. Right, okay. And then in a closed circuit, what happened? We know that our EMF now, which is our maximum, in this case was 12 volts. But when we close the switch, as it is shown in the circuit alongside, we obtained a V external of 9 volts. So what happens here, if we close the switch and measure the voltage across the battery, this gives us the external voltage, which is equals to 9 volt. Now, the lost voltage is actually 12 minus 9. So in other words, V lost, okay, or V internal, all right, sometimes we would refer to as V internal, is actually equals to EMF less V external, okay, which is what gives us the lost volts of 3 volts. Okay, so our V internal in this case is equals to 3 volts, right? Okay, and then when the switch was closed, we also identified that the 9 volts is divided. Okay, as actually the 12 volts, which is the maximum, is divided between the external voltage and the internal voltage, which is why we are saying that 12 is equals to 9 plus 3. Okay, this is in terms of voltage, right? But what do we know? We know that according to Ohm's law, we know that V is equals to the product of current and resistance. This is with respect to the external circuit. But in as far as the internal circuit, we know that V, so this is external, okay? So V internal will be then equals to current multiplied by the internal resistance, right? So hence it gives us that equation. Okay, we can express this equation by applying the Ohm's law, right? Okay, then when we do that, we can also say, right, we are able to say, okay, if in this case, this is for external voltage and that is for internal voltage, we can say current is the common factor here. We can talk about this in terms of, you know, the product of current and resistance. And if you look at it, this is like V is equals to I multiplied by R, because that is resistance, this is current, that's voltage. So this, we're still applying the Ohm's law when we say E is equals to I R plus R, okay? So this is actually the resistance of the circuit, both you know, of the battery as well as you know, the external circuit in this case, which is the bulb, right? So these are different, these are variations of, you know, the EMF equation, right? That's how we would actually apply it. So whether you choose to look at it in terms of E is equals to V external, okay, plus V internal. It's the same as saying V is equals to I multiplied by R plus R. But why is I a common factor? Because the current that goes through the battery, okay, we're talking in terms of internal resistance, will be the same as that which goes through the external circuit, in this case, which is the light bulb, because these are actually in series, right? That's why we talk about the sum of the two, okay? So in as far as that equation is concerned, I think it's very, very clear. So when the switch is closed, we can apply the Ohm's law. So if you think of the importance of the Ohm's law, is that we need to understand the Ohm's law so that we can correctly apply it. And then why do we add the resistance of the light bulb to that of the battery, which is the internal resistance? It's simple. We're talking about resistors in series. Okay, so if two resistors are connected in series, their effective or equivalent resistance is the sum of the two, which gives us the big R plus the small r, okay? And also, they receive the same amount of current. That's why we managed to factor out the current, because it's the same amount of current in a series circuit, right? All right, so we are simply saying the equation E is equals to I R plus small letter r is actually an application of the Ohm's law, which is V is equals to I multiplied by R, right? So these are some of the very important concepts in as far as, you know, the application of the Ohm's law. Now, we'll take a short break for now. When we come back, we'll look at typical circuit problems and see how we work around, you know, your internal resistance, your EMF, you know, your current. So we'll try and make use and apply this equation in solving problems. Let's take a short break for now.